Hello everyone, I am Yi-Chiao from Nagoya University, Japan. Today I would like to introduce our work, Quasi-Periodic Parallel waveGAN vocoder, a non-autoregressive pitch-dependent dilated convolution model for parametric speech generation. This is my outline. First, I will briefly introduce parallel waveGAN. Then the proposed quasi-periodic parallel waveGAN is presented. Last, I will give some discussion about our method. As we know, speech is a sequential signal with a very high temporal resolution. The sampling rate of a speech signal is usually higher than 16K Hz. So it means that we need to model more than 16,000 sample points in 1 second. Since most people speak 1 or 2 words in 1 second, the correlation of a very long sequence should be modeled. WaveNet and parallel waveGAN are two state-of-the-art speech generative models. WaveNet models the probability distribution of each sample, conditioned on previous samples and acoustic feature H. PWG directly transfer Gaussian noise Z into speech samples, conditioned on acoustic features too. Therefore, the input of WaveNet are previous samples, and the input of PWG is Gaussian noise. The output of WaveNet is the probability mass function of each sample, and the PWG directly outputs speech samples. The region of previous samples affecting the output is the receptive field, and the receptive field length is highly related to the model capacity. To attain long receptive fields, WaveNet adopt an autoregressive dilated CNN-based model, and PWG adopt a non-AR DCNN-based model with a GAN structure. The main advantage of the PWG is the real-time generation because of its non-AR mechanism. However, as we know, speech is a quasi-periodic signal. The periodic component has a long-term correlation, and the periodic component has a short-term correlation. Therefore, a fixed network architecture without prior knowledge of audio periodicity is inefficient. For example, as shown in this figure, the fixed receptive field length and sampling sparsity make the network oversample the periodic signal, which means the receptive field includes many redundant samples. Furthermore, because of the data-driven nature without prior knowledge of pitch, when conditioned on unseen acoustic features such as scaled pitch, it is difficult for the PWG to generate speech with an accurate pitch. Here are some samples. First, I played a sound with normal pitch. The first one is natural speech.
The hills ran up clear above the vegetation in spires of naked rock.
The second one is PWG generative speech.
The hills ran up clear above the vegetation in spires of naked rock.
The third one is our proposed QPPWG generative speech.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that both PWG and QPPWG generative speech are very similar to the natural speech. Secondly, I paired the sounds with double pitch. The first one is what we expected.
The hills ran up clear above the vegetation in spires of naked rock.
The second one is PWG generative speech.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that the speech quality has become much worse, and the pitch is much lower than what we expected. The third one, I paired our proposed QPPWG generative speech.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that although the speech quality is still degrade, it's much better than PWG generative speech. And most important is that the pitch is more consistent with what we expected. The core of our proposed QPPWG is PDCNN. As we know, the main drawback of CNN or DCNN is the fixed geometric structure. Specifically, a convolution with a size 3 kernel is formulated like this equation. Y is feature map, I denote input, and O denote output. WC, WP, and WF are weight metrics for current, past, and future samples. T is the time index, and D is the direction size. For CNN, D is set to 1. For DCNN, D is predefined and time invariant. However, for our proposed PDCNN, the direction size D prime is pitch dependent and time variant. The original direction size D is multiplied by a time variant pitch dependent scale E to get the direction size D prime of PDCNN. With the pitch dependent direction size, Each sample has a specific effective receptive field length corresponding to its pitch. For example, as shown in this figure, although signals A and B have different frequencies, by changing the sparsity of the CNN sampling grid, their effective reset field still contains the same number of periodic cycles. Furthermore, we propose a QP structure to model the quasi-periodic signal. The QP structure is composed of cascaded fixed and adaptive blocks. The fixed blocks with fixed network structures adopt PDCNNs to model the short-term correlations of a periodic component. The adaptive blocks adopt PDCNN to model the long-term correlation of periodic components, and its network architecture is dynamically changed according to the input pitch. We apply the QP structure to the PWG. Since the discriminator and the multi-STFT laws show the effectiveness in the PWG training, the proposed QPPWG inherit them. The main difference is the QP structure applied to the PWG generator. The original PWG includes 30 fixed blocks, but the proposed QPPWG only includes 10 adaptive and 10 fixed blocks. Because of the more efficient speech modeling, the QPPWG reduced 30% model size of PWG. For the experiment, both VCC 2018 and partial CNU-RT corpus were adopted as the training corpus. The total data length of the training corpus was around 2.5 hours. For the testing, the spoke set of VCC 2018 was adopted. The acoustic features were extracted by word vocoder. For pitch accuracy, we first conducted objective root mean square error of log F0. The results show that the proposed QPPWG achieved higher pitch accuracy than PWG when conditioned on scaled F0. Moreover, we also conducted subjective ABX test. At each try, we play a reference utterance and 2 test utterances. The listeners should pick up the test utterance whose pitch is more consistent with the reference. Since we don't have ground truth of natural speech with scaled F0, we take the word-generated speech as the reference. According to the result, we can find that QPPWG also attains perceptually higher pitch accuracy than PWG. For speech quality, we conducted MOS test. According to the result, we can find that QPPWG outperformed the same size PWG and achieve comparable speech quality to the larger size PWG in all scenarios. QPPWG even outperformed the larger size PWG in scaled F0 scenarios. Furthermore, according to the visualized intermediate output, we can find that PWG gradually generates both harmonic and non-harmonic components. However, the QPPWG with an adaptive to fixed order first generate the harmonic component and then the non-harmonic component. However, the QPPWG with the reverse fixed to adaptive order first focus on non-harmonic component and then generate harmonic component. The result confirmed our assumption that the adaptive blocks modeling the pitch-related component with long-term dependency, and the fixed block modeling the spectral-related component with short-term dependencies. Although QPPWG is trained as a unified network, the adaptive and fixed modules works like a source filter model. There are some samples. First, I play the natural speech.
And was just in time to see it pop down a large rabbit hole.
Secondly, I play the sound of the QPPWG fixed blocks. The first one is the result of half pitch.
It was just in time to see it pop down a large rabbit hole.
The second one is normal pitch.
It was just in time to see it pop down a large rabbit hole.
And the third one is double pitch.
It was just in time to see it pop down a large rabbit hole.
We can find that the output of the fixed blocks are similar. The result indicates that the fixed blocks mostly focus on pitch-independent components such as spectral envelope. Last, I played the sound of the QPPWG adaptive box. The first one is the result of half pitch. The second one is normal pitch. And the third one is double pitch. We can find that the output of the adaptive box are pitch dependent. The result indicates that the adaptive box mostly focus on pitch-related components such as excitation signal. The cascaded QP structure works like a source filter model. Furthermore, the generated speed in real-time factor was also evaluated. First, we test on a CPU with 2.6 GHz and 32 threads. According to a result, we can find that because of the smaller model, the generative speed of QPPWG with 20 blocks is faster than that of original PWG with 30 blocks. However, when tested on a GPU, because of the QP structure degrades the CNN parallelization, the generative speed of QPPWG is slower than the original PWG. However, since the generation is much faster than real time, the increased time is insignificant. In conclusion, the proposed PDCNN is very simple and can be easily integrated into any CNN-based model. The proposed QP structure makes a pitch adaptive network available, and its source filter-like architecture is more tractable and interpretable. Compared with original PWG, the proposed QPPWG achieves better pitch controllability and a similar speech quality with a smaller model. More details and information can be found on our demo page and GitHub repo. We also extend this work to a journal paper and put it on archive. Thanks for your attention.